Thank you, Nathaniel, and I'd like to start by thanking the KATP and also the tireless organizers of both programs. It's really been a pleasure to be here the last 5 weeks participating in both programs and going to lots of interesting talks by people from different backgrounds, talking to lots of interesting people. And indeed, I'm happy to now tell you a bit about what is part of my research program the last couple of years, trying to learn some lessons and technology from generalized symmetries and really bring it to bear on particle physics. So I'm going to be mostly talking about non-invertible symmetries and how those can teach us about naturalness, and actually mostly these first couple papers with some fantastic collaborators, Clay and Sungwoo and Kantaro. There's more recent work on axion theories with Antonio Delgado and forthcoming with Gongjun Choi, but I don't think I'll get there. And I want to also mention my collaborator, Adam Martin, 6 weeks ago was here giving a talk on this work on fractionally charged particles and the one-form symmetry of the Standard Model. So there are lots and lots of things connecting generalized symmetries to particle physics that are would be good to understand better and explore more, as Nathaniel also emphasized in his talk yesterday. Lots of exciting things to do. But actually, on the way to that, I would like to start by giving my answer to the central question of this program: what is particle theory? This is no longer working. Yes. Good. So in my view, the biggest lesson we should take from the sum total of scientific inquiry is the remarkable success. It's really not working. That was not the right thing to do. There we go. The remarkable success of reductionism. This idea that we can understand big, complicated systems by zooming in and looking at smaller scales at their constituents, and there find a simpler theory which is more predictive of the long-distance phenomena. In my view, particle physics is the continued pursuit of this strategy of reductionism, be it better understanding the theories that we have, or pushing to smaller distances, or even to larger distances in cosmology. And I want to remind you just how successful this program has been. You know, it was only less than 400 years ago that Hooke and van Leeuwenhoek built powerful microscopes and discovered that living beings are composed of cells at distances of order 10 to the minus 4 meters. This has been very important for me to understand, certainly, to say the least. And over the intervening few hundred years, we have pushed this program remarkably farther, down some 15 orders of magnitude. And now with the Large Hadron Collider, with the Standard Model, we understand what we look like on distances down to something like 10 to the minus 19 meters. Really an amazing achievement of humanity. And indeed, as we've gone down in distance, we've found a chain of effective theories that all have more and more explanatory power. We've really found simpler theories. One coarse measure of this is just looking at the number of distinct objects in these theories. At macroscopic scales, there have been more than of order 1 billion different types of cells that have existed on Earth. Obviously, far fewer organic molecules, relatively quite few atoms. And now with the Standard Model, we have this theory of nature that at its core includes only about 20 distinct entities. So really remarkable, and I think that gives us a good reason to continue to think that this continues and to reason using these ideas. And of course, I should also mention, especially for at least half the audience, that going the other direction, it's amazing that there are these remarkable emergent phenomena that occur. And that's very exciting, and I'm glad people work on understanding that as well. So how does this inform particle theory looking for physics beyond the Standard Model? Well, a first thing to say is that what you'd really like to happen at even smaller distances is, again, to find a more fundamental theory with a smaller parameter space, fewer parameters. That's the only way that you can actually have a theory that gets more and more predictive of the long-distance physics. But more to the physics, quite generally, when we come across naturalness or fine-tuning problems, these are an obstruction to writing down a UV theory that is predictive and has explanatory power. In the following sense, let me remind you of the electroweak hierarchy problem. The Higgs in the standard model, the question of the Higgs mass in the standard model, it doesn't have anything protecting the mass scale. So if you look, you can look at a particular grand unified theory to see this sharply, or just some generic UV physics that the Higgs emerges from. And what you find when you start at that high scale and you run down to standard model energies, you'll find that you need to get the Higgs mass in such a theory, which is something like 10 squared GeV, from a sum over lots of contributions all the way up to those heavy mass scales, a sum over things up to, say, 10 to the 16 GeV. Now, this is disastrous because it means that in order to get anything that looks like standard model physics in the far infrared, you need to fine-tune your UV parameters to something like 1 part in 10 to the 28. And so, to be clear, this isn't an inconsistency of a grand unified theory or something. A grand unified theory can accommodate a small Higgs mass, but it means that there's no sense in which such a theory explains the Higgs mass, because it's in no sense a generic feature of the UV theory. It's something that you need to go to some extremely special point in parameter space to find. And now, you should contrast this with our theory for the mass of the proton. We know quite generally from asymptotic freedom that if you start in the UV with QCD, the theory will generate a smaller mass scale for you. And in that sense, QCD really explains how this mass scale comes about. Okay. So, especially for the non-particle physicists in the audience, I wanted to give some take on what is the task for contemporary model builders. Well, unfortunately, it seems that the brilliant ideas that particle theorists have come up with over the past decades seem not quite to be realized in nature in the way that we thought, at least. And so really what we're looking for, what I'm looking for, is to write down some interesting natural and predictive models of particle physics, which thus far have been overlooked. And of course, we're aided in this pursuit by the last over 50 years of people thinking about beyond the standard model physics, some of the smartest people around, and what they've found, what sort of phenomenologies can exist. Of course, most importantly, we need to look at any possible empirical hint from nature, looking in any possible direction for what new physics should look like. And of course, we are generally guided by some understanding, at least, of the structure of quantum field theory, general relativity, maybe string theory, which, of course, guides what sort of phenomenologies can exist. So the point is that we have to be guided both by empirical data, obviously, that's what we want to explain, but there is all of this great theoretical data that we can make use of. And in particular, we get a lot of bottom-up guidance, very generally, toward a natural UV theory from symmetries. Okay. So let me go through an example, which is the lepton sector of the standard model. Actually, I'm going to include right-handed neutrinos in the standard model, because later I'll talk about Dirac masses, but you could do this, of course, without them. Good. So we have 3 generations of each type of fermion in the standard model, and that means that without the Yukawa couplings, you have a large flavor symmetry in the lepton sector, U3 cubed. Now, when you turn on the standard model Yukawas, you're explicitly breaking most of that flavor symmetry. And not only that, we've observed that the parameters coming from the lepton Yukawas are indeed weird and non-generic. And you might have the very general concern, maybe in the lepton sector we're going to get into this problem that we had with the Higgs, and it's going to be very hard to find any sort of UV theory that can get the lepton sector correct without enormous fine-tuning. In particular, among the charged leptons, the eigenvalues of the Yukawas are very hierarchical between the 3 generations. In the neutrino sector, we haven't pinned down all 3 masses, but at least 2 of them are around the milli-eV scale, much lighter than the charged leptons. The last one might also be at the milli-eV scale. We don't know. And In the mixing matrix, we have very large mixing in the lepton sector, unlike in the quark sector. So we see weird and different sorts of structures among the charged leptons and the neutrinos. And so, of course, what we actually want is a UV theory that explains why we get this structure. But in the absence of that, we can use symmetries to think about a question like, well, maybe these distinct structures, even if you set them up in the UV, will perturb each other as you run down from the UV into the infrared. Maybe you should actually expect to find hierarchical masses in both, or anarchy in both. Naively, you'd think maybe there is such a problem. Now, 50 years ago, 't Hooft taught us how to think about this. Of course, the Yukawas have broken this symmetry, but what 't Hooft tells us is that we can just assign these parameters a spurious charge. We can pretend that they transform as bifundamentals under the symmetry, and that formally restores the invariance of the Lagrangian under these symmetries, and then we can continue to reason using them. And quantum field theory doesn't know that these are fake charges. It doesn't know that they're actually numbers and not the background values of some fields. So whatever we compute will continue to respect this spurious symmetry. And in particular, if we look at quantum corrections in this theory, for example, just the beta function, you might worry, like I was saying before, maybe the neutrino Yukawas will change proportionally to the electron Yukawas, or the other way around, and you should only end up with one sort of structure. But in fact, from this simple argument, recognizing these as spurions for this symmetry, you know that just covariance under this flavor symmetry tells you that can't happen. The only object that can transform appropriately on the right-hand side of these running equations has to be the Yukawa itself. And at least if you set up these different Yukawas at a high scale, they are stable upon renormalization group flow from the UV to the infrared. So what's the situation in the standard model in total? Well, most of the parameters in the standard model are actually in the Yukawas, and all of these are technically natural. This tells us that these problems are easier. You can solve them at a small scale. But I want to emphasize, technical naturalness is not ultimately what we want. We want to explain these parameters, and technical naturalness is great, but it doesn't give you any insight as to a UV mechanism that might have produced these. And this is where we'll find a comparative advantage with understanding non-invertible symmetries in a few slides. Also, in the standard model, we have these even bigger naturalness questions. There's an unnatural parameter at each even mass dimension. At 0 dimensionless numbers, there is strong CP. I'll talk about that more later. I already mentioned the hierarchy problem. Of course, the worst is the cosmological constant. Good. Okay, so this argument from 't Hooft about symmetries has guided particle theory enormously over the past half-century, and recently we've learned that there are new notions of symmetries that can appear in quantum field theories. And at least in four-dimensional field theories like we think about mostly for particle physics, much of the novelty comes from considering symmetries of extended operators. When you took quantum field theory, you thought about symmetries by writing down the Lagrangian data of your theory and thinking about transformations of local fields. That's all well and good in this expanded framework. We call those zero-form symmetries. They act on point operators, and if they're continuous, they have a conserved current. But as you've learned more particle physics, you know very often our theories have in them some extended objects. These might be cosmic strings or domain walls that can play an important role in the early universe. Or, most importantly for today, just Wilson or 't Hooft lines. I'll remind you, you can think of this as the world line of some heavy electrically or magnetically charged particle. And these line operators can enjoy a notion of one-form symmetry. And a continuous such symmetry, again, is a conserved current, but now with two indices. Okay. And perhaps maybe the most revolutionary idea at the core of this generalized symmetry program is a new framework for understanding what symmetries are really fundamentally, which is that symmetries should be best understood in terms of the existence of some surface operators which are topological. And I'll tell you what I mean by that. So you'll recall, of course, if you have a continuous global symmetry, you get a conserved current, and from your undergrad classes, you remember you can integrate the zeroth component of that over a time slice to get a charge that is invariant under time translations. Well, we can generalize and covariantize that construction, in fact, to integrate the current over the normal component of any three-dimensional closed manifold. And the upgraded, the more covariant version of that time translation invariance now tells us that this operator is topologically invariant, in that if I vary my surface from sigma 3 down to sigma 3 prime, and I ask about the difference in the charges computed by these different surfaces, sorry, I missed saying, indeed, this counts the charge inside the surface. If I compare those charges, you can trade this difference of surface integrals over the current for a volume integral, a 4-volume integral over the divergence of the current. And if the current is conserved, this vanishes identically, telling you these two surfaces will compute the same charge. It only depends on it's topologically invariant under any sort of variation. Now, for the particle physicist, this might seem like something bizarre. Why would you want to do this? But in fact, you're actually familiar with a topological surface operator already in the form, in the context of one-form symmetry. And this is nothing other than what you did in some undergrad class with a Gaussian surface. There you had a picture at a single time slice, you drew a two-dimensional surface, and you integrated the electric field over it to find some sort of conserved charge, which indeed didn't depend on how big you made your surface. We can again covariantize this by integrating, in fact, f mu nu over any two-dimensional surface. And this covariant construction makes clear that actually what Gauss's law was computing for you always was a charge for a one-form global symmetry, because the appropriate object that can that has a notion of being either inside or outside a two-dimensional surface in 4 space-time dimensions is a line, a Wilson line in this case. A point operator is either inside or outside of a 3-dimensional surface. Okay, and again, you can do the same exercise of varying the surface, and you'll find a volume integral of the divergence of f mu nu, which in the long-distance limit of QED is identically 0. And so again, the surface is topological. Okay. Now, what's really, what I'll use as a key feature of understanding generalized symmetries in particle physics is actually the breaking of these symmetries. Because of course, as particle physicists, usually we're actually interested in approximate symmetries rather than exact ones. And there's a qualitative difference in how these sorts of symmetries can break. If I have a zero-form symmetry, as you know, I can explicitly break that just by adding some charged operator to my Lagrangian. I add a Majorana mass for neutrinos, I explicitly break lepton number. But for these higher form symmetries, the charged objects are not local operators, not the sort of thing that can go in the Lagrangian. And so, indeed, there's no Lagrangian deformation that you can do that will violate these symmetries. These symmetries only get explicitly broken when the operators that are charged under them can end. When you go to some further UV theory and you see new dynamical degrees of freedom upon which these operators can end. I'll remind you, in long distance QED, the only gauge invariant Wilson lines you can draw are closed loops or infinite lines. But when you go to higher energies and you see the dynamical electron, you can end one on a positron and an electron, say. And then you could just from this picture, you can ask, well, could Gauss's law continue to hold? Could this Gaussian surface continue to compute something topologically invariant? And the answer is just clearly no, because you can deform the Gaussian surface straight off the end of the Wilson line. Gauss's law has to break when you go to higher energies and you see charged dynamical degrees of freedom. And indeed, you can Well, okay. This is a very interesting feature that makes higher form symmetries more robust in a sense. You can see this by computing the corrections to Gauss's law from the Earlian potential. And in general, you might expect, well, maybe there should be power law corrections in the mass of the lightest charged particle. In fact, because what's really going on is you're breaking a one-form symmetry with the existence of this electric charge, in the low energy limit, the corrections are not power law, but they are only exponentially suppressed. They have to come from a sort of non-local effect. So this is extremely cool. We've learned there are new types of symmetries. They break in a different way. We should, of course, be looking for how we can capitalize upon this as particle physicists. Now, let me remind you that in electromagnetism, at long distances, we have both Wilson lines and also 't Hooft lines, the world lines of magnetically charged particles. Okay? And like I just went through, the electric one-form symmetry breaks when you see the lightest charged particle, the electron for us. In fact, it's actually nicer to talk about, rather than the charge that we were just computing, an exponentiated version of this charge, a unitary operator, and that also makes clear, because this angle alpha can be anything, that makes clear it's a U1 one-form symmetry. But now, also, we have, in line with your notions of electromagnetic duality, we have a one-form magnetic symmetry that breaks when you go to a further UV theory and you see magnetically charged degrees of freedom. And I'd like to emphasize, it's easy to include some dynamical electric charges. You don't learn so much about your theory, what's happening when you go to the scale of a new electrically charged particle. Of course, the one-form symmetry breaks. But magnetic monopoles only appear in our UV theory when there is some sort of dramatic rearrangement of the degrees of freedom, when you get some new notion of topology. So, in fact, if we can understand some particle physics effect that is related to magnetic one-form symmetry breaking, you learn something sort of drastic about what your theory can do in the UV. Okay, and I need to give some motivation for non-invertible symmetries, which I am getting to. So let me remind you of the mystery of the missing instantons. As you know, a zero-form global symmetry in a gauge theory can become anomalous. Even if it's a good classical symmetry, in the quantum theory, you break current conservation, you end up with an FF tilde term. And it's the instanton configurations that have a non-zero integrated FF tilde, and so can really activate this anomaly and give you the charge violation. But it turns out sometimes they don't. Most famously, a U1 gauge theory does not have enough internal richness to have instantons around empty flat space. And so the integral of FF tilde over R4 vanishes identically for any field configurations. Now, the old lesson people took from this is, well, okay, somehow the symmetry is formally anomalous, but actually, if you go and compute the S matrix, you'll continue to find that the theory preserves X. So, great, that's one fewer thing I have to worry about. But there's a better lesson to learn. And actually, we should have been severely confused about this as effective field theorists, because really you should think, if you ever compute or observe a zero, there must be a symmetry that is enforcing that zero. So there must remain some sort of subtle symmetry here. Actually, we could have always gotten a hint from the fact that this anomalous symmetry can be violated around magnetic monopoles. Yes. And so it should have something to do with the existence of those magnetic charges. And indeed, a few years ago, from Yichel and Hotat and Shuheng and Clay and Cantaro, we learned there is just such a subtler notion of symmetry. You can't do the symmetry operator that you had before, just integrating the zero-form current over it, because that's not conserved anymore due to the anomaly. Something people tried a lot is trying to make some sort of improved current by moving the right-hand side to the left-hand side, but that's not actually gauge invariant. But if you're friends with some condensed matter theorists, or people who know condensed matter theory, they will tell you that in this case, you can, in fact, construct still a topological engagement invariant operator if you integrate the current over it like normal, but you include also on the surface some topological degrees of freedom in the form of a Chern-Simons theory, which talks to the bulk magnetic symmetry current. And don't worry, none of the details of this are going to be needed in the things I say next, although there are many people in the audience who will be happy to tell you about this in detail. So this understanding leads us to this notion of non-invertible naturalness as a strategy. What's really remarkable here is that, and I should have said on the previous slide, sorry, because you're coupling both to the zero form current and the one form current, symmetry current, this single symmetry defect operator now acts both on local operators and also on 't Hooft lines, roughly by turning them into dions. And so we have this one symmetry structure which acts on both of these sorts of objects. And so this symmetry both controls the form of the Lagrangian, like we're mostly interested in as particle physicists, and we know something special about its breaking. In fact, it must break the symmetry structure when magnetic monopoles appear in some UV theory. And when that happens, any operators that were previously protected only by the symmetry must necessarily be generated. So this gives us insight as to some sort of universal way to break these symmetries, and it's a way that's quite special. What we really learn here is that if you find in your low energy theory, you do your spurion analysis, and if you find a spurion for a non-invertible symmetry in the infrared, well, this could be generated by non-perturbative gauge theory effects in a UV theory that includes the appropriate magnetic monopoles. Now, yes. It's a good question. In the absence of access to a dynamical monopole, I'm not sure you can. But knowing that this is a possibility, of course, allows us to understand interesting UV models that make use of this effect. Yes. It's baryon. It's not. Yeah, sure. In the proper standard model, it's not non-invertible. Sorry, go ahead. Oh yeah, sure. I mean, and in fact, as Nathaniel talked about yesterday, you can get. Oh, well, yeah. So indeed, the good, very much the perspective I'm going to take is I'm going to try to maximally use hints from the standard model to find UV theories. Absolutely, that's my philosophy as well. Yeah. Other questions, please. Yeah. Yes. No, so these are some probe operators, and you should consider that you're adding some auxiliary degrees of freedom. You're not actually enlarging your theory. Does that answer? Yeah. Would someone else like to add some words? That was mostly. Okay, good. Great. Any further questions? I should have said before. I mean, ask me at any time. Please interrupt me. Okay. So finally, that's a lot of introduction, but hopefully everyone is introduced. And where I'm going to go with this is to try to find some model building applications of these non-invertible symmetries, following exactly Arkadiy's strategy of really deeply examining the standard model and what that can tell us about interesting things that can happen in the UV. Now, of course, wherever I go, including at this program, people ask me, have I gotten to the hierarchy problem with generalized symmetries yet? Not quite, but I'm working my way there. I'm going to tell you about our first work, which was understanding a natural origin for the neutrino Yukawas, which are already technically natural, but ludicrously small, and then understanding a natural origin for small theta bar, which is, of course, unnatural. More recently, I've been filling out this column in axion theories, but I'm happy to talk about that later, but won't get to it during this talk. So we want to go beyond the standard model, but we want to stay close to the standard model. What we're going to do is we're going to gauge some of the approximate U1 symmetries of the standard model. This is something that's been worked on a lot. And let me remind you, we have a chiral gauge theory, 3 generations of fermions. The quarks, the 3 different generations of quarks carry, for historical reasons, baryon number. The 3 different generations of leptons carry lepton number, slightly more sensibly. And I'll remind you, gauging some of the approximate symmetries here, and then having them broken, of course, upon the RG flow down, is not at all exotic. You know, minimal grand unification like SO10 works because you gauge an approximate SO10 global symmetry of the standard model fermions. Okay, and we do, of course, have to. We can't gauge arbitrary combinations of these U1 symmetries. We have to worry about the ABJ anomalies that are present in the standard model. But in particular, there are some interesting combinations to gauge, which are differences of lepton or quark family symmetries. Because the gauge charges of the standard model are universal, the anomalies of one generation always cancel out the anomalies of the other. And you definitely can gauge these. Okay. So first, into the lepton sector. So I already sort of said this, but again, charged leptons very hierarchical, neutrino mixing very anarchic, very strange compared to the quark. Yes. So I make what? You have to promote dynamical field? Not quite, but you have to start in a limit where anything violating that symmetry isn't there, right? It's a gauge symmetry, so now you can't have something violating it, and you have to, whatever coupling or whatever violates it in the infrared, you need to generate upon RG flow down. Yeah. Extra gauge boson, so associated with gauge. Sure. So we spontaneously break the extra gauge symmetry, those extra bosons are heavy, and we have to go to the LHC or hopefully the FCC to find them. Yeah. Very good. Okay, but the big question is why in the world are neutrino masses so small? Comparing the heaviest neutrino to the heaviest charged lepton, it's a hierarchy of something like 10 orders of magnitude. It's okay, the neutrino masses are technically natural, fine, but that's a ridiculous hierarchy, and we'd like to understand it. And so, where I'm going is that non-invertible symmetries will guide us to some weakly coupled 4-dimensional theories where non-perturbative violation of a classical symmetry automatically gives you exponentially suppressed neutrino masses. I'm going to talk about the Dirac case. The Majorana case is actually also very interesting. We talk about it in our paper. I'd be happy to talk about it later. But Dirac, you know, if neutrinos are Majorana, then they're clearly different from the other fermions, and so people are more familiar with ways to get a small Majorana mass. Getting naturally small Dirac neutrino masses, I think, is a bit more unusual, and so I'm going to talk about that. So we're going to go beyond the standard model by gauging L mu minus L tau, the heavy gauge boson we often call a Z prime. And I'm also going to include right-handed neutrinos. And once I've gauged L mu minus L tau, there's a new anomaly diagram for me to look at. And whatever symmetry has a mixed anomaly with L mu minus L tau, an ABJ anomaly, because this U1 gauge theory does not have instantons on R4, becomes a non-invertible symmetry. And actually, whether or not you have the right-handed neutrinos, there's a Z3 symmetry. If you only have the left-handed neutrinos, then it's just a Z3 subgroup of lepton number that obviously disallows the Majorana masses. If you have the right-handed neutrinos, this gives them the opposite of their lepton number charge and disallows all of the mass operators, or in other words, even the Dirac neutrino Yukawas become spurions for this non-invertible symmetry. And so the model building logic now, understanding something about non-invertible symmetries and their breaking, is we have in our infrared theory a classical global symmetry that protects some operators we care about, these Dirac neutrino Yukawas, and it has an anomaly with our gauge group. But while on a general space-time or a general field configuration, you can have integer instantons here, on R4 there are no instantons, and so this X becomes a non-invertible symmetry. And from understanding the symmetry breaking, that means that if we go to a UV theory that includes the appropriate magnetic monopoles, we can have these operators be classically absent and generated only by instantons. Okay. Oh, I should say the connection between, before I talked about non-invertible symmetry breaking in terms of introducing magnetic monopoles, we will find in the UV that it comes from instantons. The connection between these two pictures was very nicely discussed last week by Isabel Garcia. And I refer people to that talk as well. Great. So it's not automatic. There isn't a unique choice. You still need to be a good model builder and particle physicist and quantum field theorist. But with this infrared guidance toward this UV theory, you can find the simplest way to do this is to simply embed L mu minus L tau in an SU3 non-abelian lepton flavor gauge theory, where you you just group together the three generations of each kind of lepton into the fundamental or anti-fundamental of this gauge theory. And indeed, what you can do in this theory, as we knew from the bottom up we must be able to, you can write down in the UV only the charged lepton mass, charged lepton Yukawa. Of course, it's flavor symmetric. I haven't written the indices. And there's a classical symmetry that protects the Dirac neutrino Yukawas. But as you run down in energy and break SU3, you find that the instantons of this lepton-flavored gauge theory generate for you a Tuft vertex, which gives you precisely the Dirac neutrino mass operator coming from the charged lepton Yukawas, but suppressed by an exponential of the instanton action. And so automatically, structurally, generically, you get very suppressed, exponentially suppressed neutrino masses compared to the charged lepton masses. Indeed, I think quite such a robust explanation for Dirac neutrino masses perhaps had not before been seen in weakly coupled four-dimensional gauge theory. So I was very pleased to be able to write this down. And since it's such a simple theory, it's very economical, it's very predictive, if we were to discover a Z prime for L mu minus L tau tomorrow at the LHC or sometime in the future at a muon collider, what have you, you would in fact learn the scale at which the rest of the non-abelian gauge bosons should reside. And of course, the particle physicists are about to object to me. I should disclaim, indeed, all I've done by using these flavor-symmetric instanton dynamics is to generate an overall Dirac neutrino mass scale that's very exponentially suppressed. Of course, we need to get the texture. You can get that from the Higgsing down from SU3 eventually back to the standard model. And actually, this was studied in almost this theory by Gonzalo Alonso Alvarez and Jim Klein. I'll refer to that paper. The eigenvalues, yeah. But indeed, it's not too bad. Yes, but it would be really great to explore this further. Of course, to make realistic contact with the lepton sector that we've observed. Okay, I think from here I'm going to go now to the quark sector. Any further lepton questions? Okay. Oh, of course. In fact, that's how we found it, right? I found a non-invertible symmetry in the infrared. I said this has to be broken when you introduce magnetic monopoles. And indeed, we found that actually from the UV perspective, the breaking comes from these instantons. That's exactly right. Yeah. Okay. Again, so the texture I have not addressed here, you need to get that by RG evolving down. Of course, as you know, L mu minus L tau is often studied precisely because it enforces large mixing. So I don't think it's too bad. Yeah. but indeed, yes, would be really fantastic. My background is not actually flavor model building, so I've been a bit slow on the pickup there. But it would be really great to make these theories more realistic. Good. So, like I mentioned, in fact, in our paper, we go through both the Majorana and the Dirac case. It's a quite interesting Majorana mass model. You could get TeV scale physics generating the neutrino Yukawas, and it's not seesawed. It's exponentially suppressed by the same sort of instance-on factor. Yeah, both theories are interesting. Yeah. So, as we were working on this neutrino non-invertible neutrino mass project, I was convinced, well, once you add the right-hand neutrinos to the standard model, there's a structural parallelism between the quarks and the leptons. The quarks are really just the leptons with color. And so I was convinced that there had to be something to find also in the quark sector. And indeed, it turns out that understanding non-invertible Peccei-Quinn symmetries allows us to say some interesting things about natural UV completions of all of the most parsimonious strong CP models. But I'm only going to get to the first one. I'm happy to talk about the axion cases later. So let me briefly remind you what strong CP is. This merits a much longer discussion, but okay. So in a pure gauge theory, we have this topological angle that's CP odd. Now, the standard model has some very non-trivial structure of colored fermions, and so, in fact, the field redefinition invariant CP odd parameter of the strong sector in the standard model is the imaginary part of this complex number m, which combines the strong angle with the determinants of the up and down quark Yukawas. And remarkably, we've looked for this in neutron EDM experiments and have not detected a neutron EDM yet. We found that this parameter, which could be a generic complex number, is incredibly close to the real axis. Very surprisingly. And it's even worse. You can't just solve this by saying, well, maybe by immediately saying, maybe the world is actually just CP symmetric, because elsewhere in the quark Yukawas, there is large CP violation, sort of associated to the weak sector. Just this different combination of the Yukawas, that there it really is just a generic complex number. And so it seems very strange and not technically natural that we have these very different CP violating parameters. Yeah, to connect to language people often talk about, theta bar is just obviously the angle between the imaginary and the real parts. But I'm not talking in theta bar because the massless quark solution, the most parsimonious way that strong CP may have been solved, it has a Peccei-Quinn symmetry that pins m to 0. And we won't spontaneously break this Peccei-Quinn symmetry, but we'll find that QCD generates a non-zero m that's automatically along the real axis. And maybe a quick rant. People sometimes say that the massless quark solution makes theta bar unphysical. And I think that's really silly and confusing because it's just a coordinate singularity. Obviously, if you start, you have to say, like, you start with this parameter unphysical, and then standard model quantum corrections generate some real non-zero value. Very silly. Think about it in the Cartesian plane. It's less than 10 to the minus 10. Well, sorry, you're right. I haven't. Okay, you're right that just this statement loses that information. The statement, if m is non-zero, the statement is that it's close to the positive real axis, really. Yeah. Good. Okay. So let me remind you of how the massless upquark solution works in slightly more detail. For simplicity, let's just think about one generation of standard model fermions, and we're going to impose in the UV a Peccei-Quinn symmetry under which only the right-handed upquark transforms. And this means that in the UV theory, you can only write down the down quark, and in generic basis also the theta parameter. But because we have this good anomalous symmetry, you can in fact use the freedom of up quark rotations to put it into a form that's manifestly CP invariant. Of course, it's CP invariant whatever basis you have it in, but just manifestly you can get rid of the theta angle. And then, of course, the up quark in the far infrared we've known for many decades is not massless, but that's not a bug, that's a feature of the solution because it's an anomalous symmetry. So as you flow down in energies, instantons generate for you a non-zero up quark that, just like before, comes from the down quark Yukawa and an instanton factor. Now, the standard model is actually much more complicated than this because we have 3 generations, so lots more legs here that you need to close off, and also because the most important instantons are at the scale of confinement where we lose control. But thankfully, lattice physicists have been on the case, and really heroic efforts over the past few decades have now told us the standard model unfortunately does not bear out this massless up quark solution. We don't live in the right point in parameter space. But now we have some symmetry-based tools to point us to UV models that have interesting instantons, and so you could ask about reviving this solution. We're going to proceed analogously to the lepton sector, but let me note that adding a quark flavor Z prime, gauging some U1 symmetry there, can be more subtle because of this special coincidence that we have the same number of colors of QCD as generations of fermions. And this means that when we go and gauge a Z prime like B1 plus B2 minus 2B3, there's a special possibility to have some shared global structure with SU3 color. If you haven't been thinking about this, the quotient here tells you that you're identifying a Z3 subgroup of both of these different factors. So if you go far away from the origin in like the color gauge group, you end up in the flavor gauge group, in fact. Okay. Now, I don't have time to, well, okay. So at intermediate scales, in fact, you could continue proceeding as in the lepton sector. If there's also a non-trivial global structure you can have with the full SU3 flavor symmetry of the quarks gauge. And in fact, you could have, it has non-trivial global structure. You could have seen this by noticing the strange fact that the quarks have the same quantum numbers under the flavor symmetry and the color symmetry. And having a gauge group with this quotient changes the topology of the gauge group. And I don't have time to go through this very pedagogically, but in particular, when you have non-trivial such global structure, there are fractional magnetic fluxes that can appear on a general space-time, and fractional instantons, no longer only integer-valued instantons. And so, in particular, in this case, you find instantons with instanton number in an integer over 3, and this diagonal quotient locks the fractional parts of the color and the flavor gauge group instanton numbers together. And the non-invertible symmetry analysis you need to do in this case is just a little bit more subtle. You have to look at your classical global symmetries and ask about mixed anomalies they have. First, in integer instanton backgrounds, any with such an anomaly are just broken. But if they have an anomaly only in these fractional instanton backgrounds, which I should say, again, don't happen on R4, but only on some, in empty R4, but only when you have 12 lines or some 2 cycles on your space-time. If it only has an anomaly in the fractional instanton background, it becomes a non-invertible symmetry. And in fact, what you get in this case is a non-invertible Z3 symmetry, or the meat of it is a non-invertible Z3 symmetry, which is closely analogous to the lepton case. You have baryon number charge for Q and U, but you assign D the wrong charge. This is a non-invertible symmetry, and in particular, all of the down-type quarks are spurions for this non-invertible symmetry. Okay. So again, we can do our same model building logic. We've found a classical global symmetry that protects some operators we care about. It has an anomaly in our gauge group, but some of the instantons that can generally exist are not present in empty R4. This tells us that this is a non-invertible symmetry, and again, if you go to a UV theory that includes the correct now color flavor monopoles, you can start with this operator classically absent and generate it only by instantons. And so, in fact, the beautiful thing to do is to put together the 3 colors and 3 generations of each type of fermion into the fundamental of an SU9, or anti-fundamental. You don't need to add any new fermions. Indeed, what you can do in the UV, as we knew from our bottom-up discussion, you can start with only the flavor symmetric up-type quark. I put the top U power there. And just like before, you have a good Peccei-Quinn symmetry, and so there's no strong CP violation. But then, as you flow to low energies, the Topf vertices of this theory generate for you a down-type quark Yukawa. And compared to the standard model Topf vertices, here we only have, everything's unified, so now we really only have this one generation sort of Topf vertex. We don't have to close lots of lines, and in fact, because SU3 is wrapped up sort of non-trivially into this SU9, you actually get a boost by a factor of 3 in the gauge coupling in the SU9 theory, and so automatically you can have some stronger instanton effects. No, the quarks are vector-like. Yeah.
So this SU9 cross SU cross U1, that's the case.
Yes.
So there's no other mixed case number?
I don't believe so. Can I do the math in my head? Yeah. 2 minus 4 plus 2 is 0. Hypercharge.
The currents that are color cross
I'm gauging the vector-like subgroup of the flavored of the U3 flavor symmetries. Yeah. Okay.
Standard model in principle you could have this electrolyte theta, which is not effective, standard model.
Yeah, this.
But I'm not sure if here could be effectively 2 thetas.
Well, there are. I haven't touched the electroweak part of the standard model at all, in fact. But that they're separate stories. Yeah. Okay. I'm at the end. I'm over time probably. There's lots more pheno to do here. Something I find very intriguing is that you can actually unify these quark and lepton pictures into an SU12 sort of flavor-enriched Patti-Salam model, and in there you have all of the standard model fermions in a single irreducible representation. I think that's quite interesting, and in particular, you can have quark-lepton unification consistently with, at an intermediate scale, having separate gauge, quark, and lepton flavor symmetries. So I think there's just sort of this structural, natural possibility there to end up with different flavor patterns in the quarks and the leptons, as we've observed, but really more needs to be done on writing down some beautiful flavor schemes here, although we have, and I can go into it if people ask, we have a proof of principle for generating the CKM matrix that you need consistently with keeping theta bar equals 0. And I think there's lots of interesting work also out in the sky. In the early universe, these sorts of models, you will get flavored topological defects that, to my knowledge, have seen essentially 0 study. The phase transitions could have interesting effects. You have a good UV reason to have flavored dark matter. I think there's lots of exploration that should go around these models. And last but not least, in this sort of theory, despite quark-lepton unification, the proton can be exactly stabilized by a discrete flavored gauge symmetry that resides in it, which I think is quite an interesting feature in. Yes. So I need to think. Yes. Yes.
That the instantons of that whole gauge group only preserved at the Z2 variant.
Sorry, is that true? You have 3 generations still. And so you'll get an NG in whatever calculation you're doing.
I think it one traces all the way down to Z2, like SU5 or SU5.
Sorry, from an anomaly?
No. From you can see
Oh!
the full, not the anomaly shining up. What is the full, there's the instantons shining down. Yeah.
Well, yes, but still, any anomaly diagram you compute, you sum over all 3 generations, right? I think, in general, even, okay, it doesn't quite make sense to me, but yeah.
Then it's not obvious, but okay, so.
I think there's a lot, yes, we should discuss. There is a lot of literature that says they're working in the standard model, but really only has 1 generation. But okay.
The claim is that the full anomaly 3 subgroup with high Islam of B plus L is smaller than the
I mean, that might come from some interplay with some perturbative breaking. Okay. Yeah, anyway, yes, I am at the conclusions. Let me give you my conclusions because it's 2025 and you have to back yourself. I've been really amazed using these new tools from Generalized Symmetries to really find, using the data of just some integer invariants of the standard model fermions that is always there, we've been led to some new unified theories that can resolve some naturalness issues in a very rigid and structural way. And more generally, I think any place, at least, that non-perturbative effects might be relevant, generalized symmetry should offer us some better understanding, and there's lots more exploring to do. But my big lesson that I take away from this is that as particle physicists, we are not yet done learning about the role of symmetries in our theories, and I look forward to continuing to learn more in that direction. Please. Yeah. No, very good. And indeed, that is something that is sorely needed because, in fact, just like in the up quark solution, actually where you end up in parameter space to get large enough down-type quark Yukawas, the 1 instanton is no longer trustworthy. So indeed, I had a nice conversation with Ethan Neal earlier from a lattice physicist at Colorado, trying to push some group at least in the direction of looking at these Higgs lattice gauge theories. Yeah, definitely something that's needed.
Can you speculate irresponsibly about what this framework might tell us about solving dimensionful naturalness problems like hierarchy problems?
I think more innovation is needed, and probably an understanding from formal folks about even more subtle sorts of non-invertible or other generalized symmetries that can exist. Solving the hierarchy problem with this sort of non-invertible symmetry logic would naturally fit into something like classical scale invariance, which people write about, but is sort of silly because we have gravity, if not any other scales in between. So I do have some thoughts I'm going to keep to myself about directions to go in. Sorry, but nothing concretely materialized yet.
Maybe I could just throw a suggestion out in the void in case anyone finds a way to make use of it. So we normally say, right, that one of the ways of understanding the Higgs naturalness problem is that there's no symmetry that's restored from Higgs mass goes to 0. But in the standard model, there is a symmetry, which is the electric one-form symmetry.
Sure.
Like once you give masses to the charged particles, which happens when you're collecting symmetry, then the one-form symmetry becomes far infrared.
Sure.
So maybe there's goodness knows how you turn that into a hierarchy mechanism. Yeah. But it is interesting that recognizing the existence of higher symmetries tells you that there is a symmetry restoration associated with
I mean, yeah, the problem.
Yeah, it's emergent. Yeah, yeah. So, but now the question is, can you make? Yeah, I mean, so this is part of my question about what is the generalized scientific paradigm of like, particularly with emergent higher form symmetries, when do they count in one as opposed
Yes.
to that?
Yeah. The problem, of course, is that QCD also breaks electroweak symmetry, and so it's not a unique spurion for electric one forms. I mean, it's still an interesting direction. Sorry, but yes.
It is a
Yes, I agree.
switch from the statements that they know.
I agree. Yeah, good. Michael?
So let's talk about generating CKM matrix.
Yeah.
SU9.
Yeah.
So, so there's this Wolfenstein parameterization,
Oh,
which has
God.
parameter lambda.
Yeah.
And different elements are lambda, lambda squared, lambda.
Yeah.
Is there an interpretation of that within SU9? That's not solving the whole theory.
Well, I haven't, again, so my background is not flavor physics. We have not written down a beautiful scheme that lands you on this sort of structure. We did find there's something interesting you can do because you have this gauged flavor symmetry if you communicate flavor breaking and CP violation to the quarks via some adjoint fields. In fact, you can automatically generate Hermitian complex, but Hermitian Yukawas in a very nice way. So because they're complex, you can get the CKM, well, this model requires a lot of tuning to get the CKM matrix correct, but you can at least get the CKM phase in a way that structurally protects the theta bar still. Yes, I mean, I can say more, but.
If this sigma matrix has some structure in it, get a Wolfenstein-like parameter.
Possibly. So the other problem is that the quarks don't, or either the quarks or the leptons don't really want to be proportional to the identity matrix, which is where you start off. Now, okay, fine. I think the right direction to go in, at least in the quark sector, if not the lepton sector, is to think about upgrading the Higgses to from singlets under the flavor symmetry to singlet plus adjoint, and then trying to find the light Higgs as a particular direction in there. But I haven't written down some such beautiful theory yet. Yeah, it's a very important thing to do, obviously. Arkady?
Of everything, whatever, where everything could be defined.
Yes.
But this belief could be,
yeah, I mean, I think.
It's an assumption by itself.
Well,
right?
we know that there are higher scales. We have gravity. We have the Landau pole of hypercharge. We know that there needs to be some new stuff. Well, we have even neutrino masses that tell us it. It could. So indeed, you see these papers that come out on the archive that essentially make the point, well, you can solve the hierarchy problem by just imagining the Higgs mass is always an input parameter. Great. I mean, but sure. That's technically true, but very unlikely to be the way that the world actually works, in my view. Yeah.
But still, in this sense, I think it is technical. Because
Yes. I started off talking about reductionism. Yeah, absolutely. It doesn't. It could all be fine-tuned. That's very possible. Well, that is conceivable, at least. I don't think it's very possible. Yeah. Good. One more. Yeah. Uh-oh. Yeah.
And there's a question to these new symmetries, once they interact with, a supersymmetric theory or something, we can say new things about concentration, how
Yeah.
about this,
I have thought about it a bit, in fact. In fact, this paper that I wrote with Antonio Delgado about the most beautiful model of an axion, most parsimonious model of an axion, the Pechiquin-Weinberg-Wilczek visible axion, started off because I wanted to try to solve the mu problem in the MSSM. And the problem I ran into, which eventually had me retreating to the non-supersymmetric case, is a detailed enough understanding of supersymmetric instantons, and in particular, like the ADS superpotential, away from the very simple case where the symmetries entirely tell you what form it has. I think it's a really interesting direction, as I've been following Arkadiy's strategy of starting with the standard model and then going to minimally more complex. Supersymmetry is definitely an obvious direction. I think there should be work toward that.
Another fantasy that would be useful to get people to think about, right, is we started making progress on nearly supersymmetric field theories 20 years ago, and then we abandoned that because we couldn't argue this. Of course, if there's any other control we get over that transition, that would be the most efficient that you could do.
Yeah.
But it would require some of these new symmetries to interact with some of supersymmetry generators.
Yeah. Yeah. Good.
So that's it for what is particle theory. So to paraphrase Douglas Adams, so long and thanks for all of this.
Yes, and of course we should thank Nathaniel for his fantastic, and Aida for fantastic organizing of this entire workshop. Thank them again, please. Oh, no,